Assalamu alaikum wa rahmatullahi wa barakatuhu. Alhamdulillah. Wassalatu wassalamu ala ashrafil anbiya wal mursaleen. Amma ba'd. This is the 7th lecture in the lecture series of the steady state errors. And in this lecture, we will study the effect of disturbances on the steady state errors. So now we can discuss that if this closed loop is stable, and it is not necessary that G1s and G2s are stable transfer functions. We need only the complete closed loop is stable. If it is not stable, any disturbance or the reference input will give us an output which will diverge. And in time domain, you know that we can write this R of t, this will be d of t, and here we will have c of t. So what happens, like if the closed loop is, this closed loop is suppose unstable, then any input d of s in Laplace domain or d of t in time domain, similarly r of t in time domain, if we give it to the system, the output c of t will diverge. So always whenever we are discussing steady state, we should take care of this fact. So now the first thing, it is better to write down the relationship of the Cs and the d of s to study the effect of d of s on the e of s. So to do this, first thing I can write that c of s is equal to C of s is equal to G1s, G2s and into E of s. So it will give us G1s, G2s into E of s, plus we will have G2s into D of s. So because this D of s is passing through the plant only, while E of s is going through the G1s, the controller transfer function, and the plant transfer function. Now a little bit simplification is required. So to do that, we know that E of s, the error, is equal to R of s minus C of s. Now if we consider this is equation number 1 and this is equation number 2, and we can insert the value of C of s from here to this equation. So here we will be getting E of s will be equal to R of s minus G1s, G2s into E of s plus minus G2s into D of s, and then this we can shift from the right hand side to the left hand side. We can bring it here. So here you will see that it will become 1 plus G1s, G2s into E of s will be equal to R of s minus G2s D of s. So then we can say that E of s is equal to Rs upon 1 plus G1s into G2s. If you want, like in proper format, we say 1 into 1 over Rs, 1 into R of s, and here we can write minus G2S divided by 1 plus G1S G2S into D of S. So the relationship of the E of S with the RS and D of S is somehow like this. So here it is clear that D of S has an effect on the E of S, and this detailed thing we will be studying in the next slides. Here the typed version of the solution is somehow like this. So we write all those equations again. So we insert, and at the end we will get this relationship. So this means the E of S is affected by R of S and D of S. So on the next slide we discuss what will happen to them in the steady state. So in the steady state, you know that fundamentally what we will have to do, we just have to find out the steady state error. What we say, E steady state and E steady state or ESS is equal to E infinity, and normally we use the final value theorem, S tends to 0 as E of S, and this will be possible only if like this system have poles, zeros in the left half S plane. So here we discuss from the previous slide that E steady state ESS is equal to limit S tends to 0 E of S, and previously we studied that limit S tends to 0 E of S is equal to 1 over 1 plus G1S G2S into R of S minus G2S upon 1 plus G1S G2S into D of S. So this is the situation. So in this slide, if we put these limits, so we will be getting ESS is equal to limit S tends to 0 S upon 1 plus G1S G2S into R of S minus limit S tends to 0 S G2S upon 1 plus G1S into G2S into D of S. Now it is very easy now to see, like this is the steady state error because of the reference input R of S, and this is the steady state error because of the input D of S. So a little bit more detail we will study in the next slides. Let's look through the typed version of this problem. So here we write like this. So at the end, like the first one is the steady state error due to R of S, and the second one is the steady state error due to the disturbance input. So here we can write these two equations. So here we see the effect of the disturbance whenever R of S is 0, and it is natural because to see the effect of D of S on the steady state error E of S, it is important that the set point should be 0 to directly see that how E of S will be affected. So at this stage we consider that R of S is equal to 0. When this is 0, this means no need for this whole block, and the block will become somehow like this, and here it is minus, and it shows us that E of S is equal to minus C of S. And we can say that C of S is equal to minus E of S. So this we will need to further see what is happening. This minus, if we bring it from here to here, so we can write over here minus, this plus will go out. So then the total closed loop will become somehow like this: G2S, C of S, and here we will have G1S, and this D of S, and here it is minus sign, and this C of S is equal to minus E of S. And then look into this block diagram, because you have studied it a lot, that the closed loop transfer function over here will be G2S upon 1 plus G1S into G2S into D of S will be equal to C of S. This means that E of S is equal to minus G2S upon 1 plus G1S into G2S, and this is the same thing what we studied at the previous slide. So the clean version of the block diagram is here. So you will see this one will be equivalent to this block diagram whenever R of S is equal to 0. So let us discuss how to minimize the effect of the disturbance on the steady state error. And when we say that minimize the effect of the disturbance on the steady state error, I mean that making this as close to 0 as possible, like this should be approximately 0. The block diagram we already discussed that is here. So for this block diagram we know that E of S will be equal to G2S upon 1 plus G1S into G2S into D of S, and here it will be minus. So to study the steady state error, consider the disturbance is a step type of disturbance. Here we are writing it is unit step, but it is possible in situation that it can be AU of t. So in that case the amplitude of the step can be other than unity, and we know that the Laplace transform of the unit step function is 1 over s. So in this situation E of s will be equal to minus G2s upon 1 plus G1s into G2s into 1 over s. Now if we are looking only for the absolute value of the steady state error, then we may remove this minus from here, no need for this, and we know that the E d infinity will be equal to limit s tends to 0 as E of s, provided this closed loop is stable closed loop. So in this case it will be limit s tends to 0 into s G2s upon 1 plus G1s into G2s into 1 over s, and s will cancel with s. So in this situation if we simplify this expression, we will get over here 1 over limit s tends to 0 1 over G2 s plus limit s tends to 0 G1s. And you know that when we are writing limit this, it means the gain of the controller gain of the controller. And here when we look, this is the gain of the plant. So whenever the gain of the plant is small, this means inverse of the gain of the plant is large, and the gain of the controller is large, the amplitude of the steady state error will be small. And this type of disturbance, step type of disturbance, occurs in many situations in control system, like in a room. If you consider your set point is 25 degrees centigrade and the room temperature was fixed on this, and someone came and he opened the door. So whenever the door is opened, first the temperature of the room will increase if the outside temperature is greater than 25 degrees centigrade, and then with some time, because of the presence of the controller, the temperature will come back to 25 degrees centigrade. Similarly, if outside temperature was smaller and there was a heater inside the room, so first the temperature will decrease and slowly it will come back to 25 degrees centigrade. So when you put in a disturbance and it remain constant for some time, we say it is step type of the disturbance. So the step type of disturbance occurs many times in the process control of the processes, which is a normal thing. So let us look to the typed solution. So the same thing in the type version is here. So here, to decrease the effect of E of D, definitely we have not written over here minus, and this minus because we are looking just to the amplitude. Otherwise, if you want to consider the minus, you should be writing. So if we want to write make this amplitude smaller, so this value should be small and this value should be large. This should be a large value, this should be a large value. So this is the gain of the controller. So large gain of the controller and small gain of the plant will reduce the steady state error in the system. So the effects are summarized here. G2S limit, this means gain of the plant. Here we are talking about this is the gain of the plant. And this one is the gain of the controller. So we need the gain of the plant should be small. This value should be a small value and this should be a large value to get small value of E of D infinity. So thank you very much. With this completes the lecture 7 of the lecture series on the steady state errors. Once again, thank you very much.